put a camera on it. It set limits on dark matter in the universe. The thing was, nobody wanted it, so if you could think of something to do, you had a free telescope. So it was a very important thing, and that's the way telescopes are sometimes. They're not necessarily dead just because they were built wrong. Photographic plates. The first picture was taken in 1826. I've seen 1822 at various times. In Paris, this is looking out a window on a rooftop. This is a picture of the moon taken in the 1840s. Picture of the sun by Foucault and Fizeau, 1845. Now, of course, these are relatively long exposures. Film wasn't very good, but this is going on while Ross is building his telescope. And it showed the sunspots that Galileo had found had come back. By 1880, people were taking pictures like you see in astronomy magazines. This is a picture of M42 in the Orion Nebula, and I've put beside it a drawing by Messier, made in the 17th century. Okay. It's interesting to look at these and see how much detail. It's really hard to understand how much detail they could pick out with just the naked eye and a small telescope. And of course, the secret is that the telescope with a piece of film on it was still very slow because this wasn't Kodak fast film. This was just the beginnings of photography. But by 1900, this is the 40-inch telescope at Yerkes, just a few hundred miles north of here. And they couldn't use a photographic plate when they started because the telescope was built to focus yellow light. But by 1900, there were films that could be sensitive in the yellow, and this is the first picture ever taken with the telescope. By contrast, 100 years later, this is the same object. You see the two stars with the red circle around them. This is the same object taken with the Hubble Space Telescope. So that's 100 years of technology. And in this picture, you can actually see all the way down to what we think are the faintest stars. The end of that story is the 100-inch reflector at Mount Wilson, built by George Ellery Hale, who went there from Chicago because Chicago had cloudy weather and California had better weather. And this has elements of everything I've shown you, and all the telescopes afterwards look pretty much like this. The questions have changed. Now the kinds of questions in 1922, when that telescope was finished. Where are the galaxies? That goes back to Kahn, Herschel, and Ross. Where do the elements come from? In the periodic table, what's the origin of the pattern in something called the Hertzsprung-Russell diagram, which you've never heard of probably, many of you, but it's the piece of data in astronomy that tells us there's real physics going on. Why is hydrogen the most abundant element in the universe? So this picture, of course, you all went through grade school, or at least high school, with it on your wall. We didn't know where the elements came from. This is the diagram I mentioned to you, the Hertzsprung-Russell diagram. By the late 1800s, because of photographic plates, people could measure the distance of stars with parallaxes, and they realized that if you try to plot luminosity, brightness versus temperature, it's not a scatter diagram. There's real pattern there. This is real physics. Understanding that was important. And then this is, I call, the astronomer's periodic table. Hydrogen is the most abundant element in the universe. Helium is next, and everything else doesn't matter. That's what you and I are made of. So why is hydrogen the most abundant element in the universe? So the telescope, like the 100-inch, were the telescopes that were used to go answer those questions, which we have largely done. And the secret was this new telescope design called a Schmidt telescope that has a corrector at the front, a reflecting surface at the back, and a piece of film in the middle. And with this telescope, Fritz Zwicky famously in the 1930s did a supernova survey, which finally led to our understanding where all the elements in the periodic table come from. That's just one example. Now we have different questions. How do galaxies form? How are stars made? What is the dark matter? Does the universe consist mostly of dark energy? These are things you read in magazines. Why are the laws of physics as they are? And are there other universes? So this is one of those galaxies, 100 billion stars. They're all over the universe. We now know, we're cataloging them. We know all about them observationally, but we don't know how they're formed. This is a hot topic in astronomy. This is a little galaxy that's doing nothing but making stars. Other places make no stars. We don't understand all that. This is one of my favorite pictures. You've all heard of dark matter. This is the stuff that makes up 6 times as much of the universe as we do, you and me, and carbon and baryons and protons and neutrons. This is a picture of the mathematically envisioned dark matter around the galaxies that we know about, and the inset is the little galaxy I've been showing you, M51. So this is a mathematical concept of what this galaxy really looks like. All the matter is basically this dark matter. And we can do the math, but we don't understand the origin of the dark matter or the origin of the structures or anything else. So this is what current telescopes are going after. And then I have these last 3 questions in red. What's the dark energy? Are the laws of physics